Everything we thought we knew about the size of the universe was built on an assumption that time, distance, and scale could be treated as simple, countable things. James Webb is showing us that assumption was wrong. Galaxies are appearing where none should exist. Structures are forming faster than physics allows. Darkness we once called empty is turning out to be crowded. In this video, we're going to follow what James Webb is actually revealing to rethink the size, age, and limits of everything we thought we understood. For a long time, the universe felt large but manageable. 13.8 billion years old. A few 100 billion galaxies. Vast, yes, but still describable with numbers that fit comfortably into textbooks. The edge of the observable universe seemed almost intuitive. Light has had 8 billion years to travel, so the farthest things we see must be about that far away. The picture felt complete. That intuition turns out to be misleading. The age of the universe is not the same as the size of what we can observe. Time and distance are linked, but they are not interchangeable. Light does travel for 8 billion years. Yet the space it travels through does not stay still while that journey unfolds. Space expands, stretches, and carries objects farther apart, even as light is moving between them. When that effect is taken seriously, the scale changes dramatically. The observable universe does not have a radius of 8 billion light years. It has a radius of about 5 billion light years, giving it a diameter close to 93 billion light years. This is not a speculative number. It comes directly from measurements of cosmic expansion. The universe is older than our intuition, and far larger than our instincts allow. For decades, this distinction existed mostly on paper. Telescopes could not probe deeply enough to make the difference feel real. Observations filled in nearby detail, but the distant universe remained sparse and dim. The early universe appeared quiet, thinly populated, and slowly assembling itself from simple beginnings. The models felt safe. That sense of safety began to erode when infrared observations reached farther back in time. When space expands, it stretches light along with it. Light emitted as energetic ultraviolet radiation billions of years ago arrives today as faint infrared signals. Instruments optimized for visible light simply miss it. Seeing deeper required not more power, but different vision. This is where James Webb enters the story, not as a protagonist, but as a measurement device tuned to the right wavelengths. Its mirrors, detectors, and operating environment allow it to collect infrared light that has been traveling since the universe was young. That light carries timestamps. Each photon records when it was emitted and how much the universe has expanded since. The first images immediately disrupted expectations. Regions of sky that appeared nearly empty in previous observations filled with faint structures. Darkness resolved into form. Smudges resolved into galaxies. What looked like cosmic voids revealed depth and crowding. The universe did not merely extend farther, it revealed more content everywhere Webb looked. This shift matters because emptiness was part of the old picture. A sparse early universe supported the idea of slow growth. Few galaxies meant few stars, little light, and gradual assembly. A crowded early universe implies something else entirely. It implies efficiency. It implies speed. It implies that the universe did not wait to become interesting, even more unsettling. These discoveries did not cluster at the edge of detection. They appeared consistently across different fields of view. Webb did not stumble upon a rare region. It sampled the early universe and found that density was the rule rather than the exception. The implication is statistical, not anecdotal. Here, the concept of scale begins to shift. Scale is no longer just how far away something is. It becomes how much exists within a given volume of space. The universe starts to look less like isolated islands separated by emptiness and more like a continuous structure layered in depth. This forces a reassessment of what looking far actually means. Observing distant galaxies is not simply peering across space. It is reading earlier chapters of cosmic history. Each increase in distance corresponds to a step backward in time. Webb does not extend vision outward alone. It extends it backward. That backward extension carries consequences. When observations reach epochs once thought inaccessible, assumptions embedded in cosmological models are exposed. Predictions about when galaxies should appear, how bright they should be, and how many should exist are no longer abstract. They can be checked directly against data. The earliest results made one thing clear. The universe was already busy when it first became visible. Structures existed sooner than expected. Light was abundant earlier than predicted. The foundations of today's cosmic landscape were laid down rapidly, not gradually. This realization reframes the purpose of the investigation. The question is no longer whether the universe is large. That is settled. The question becomes what large actually means when applied to time. Density, speed, and organization all at once. True scale turns out to be multi-dimensional. James Webb did not discover the universe's edge. It revealed how shallow our previous sampling had been. What once looked like empty background was not empty at all. It was simply invisible to older instruments. With that invisibility removed, the early universe no longer looks like a blank slate. This sets the stage for everything that follows. If the universe was already dense early on, then timing matters. If timing compresses, growth rates matter. If growth accelerates, physical limits matter. Each layer of discovery builds pressure on the next. The comfortable universe. Large but slow, ancient but orderly, begins to dissolve. In its place emerges a universe that assembled quickly, organized early, and filled space more efficiently than expected. The scale problem is no longer about size alone. It is about how much happened, how soon, and how little time the universe needed to become complex. That is the question now driving the story forward. There is a hard limit to how far back galaxies can exist. Before stars formed, there was nothing to see. No galaxies. No light sources. Only gas and darkness. This era is known as the Cosmic Dark Ages, and it lasted for roughly 150 to 200 million years after the Big Bang. During this time, the universe contained almost nothing but hydrogen, helium, and dark matter. The gas was spread out, cooling as space expanded. Gravity was present, but it had not yet won. No objects glowed. No structures shone. Even if a telescope could look back that far, it would see nothing. The moment this changed is called the Cosmic Dawn. That name is literal. It marks the first time light sources turned on across the universe. The earliest stars ignited, flooding their surroundings with radiation. From that point forward, the universe became observable. James Webb was designed to detect galaxies forming near this boundary, not by guessing, but by measuring how much their light has been stretched by expansion. That stretching is quantified by redshift, a number that directly links distance to time. A redshift of 10 corresponds to a universe about 480 million years old. A redshift of 12 corresponds to roughly 350 million years. A redshift above 14 pushes observations to around 280 million years after the Big Bang. These are not symbolic values. They are timestamps. Webb has now confirmed galaxies at redshifts above 14. One of them, known as MOM-Z14, emitted its light when the universe was only about 2% of its current age. For scale, imagine compressing the entire history of the universe into a single calendar year. This galaxy formed around January 7th. That alone would be remarkable. What makes it disruptive is not just its age, but its properties. MOM Z14 is bright, not marginally detectable, bright enough to analyze spectroscopically, bright enough to measure chemical signatures inside it, bright enough to indicate active star formation. Brightness at this distance is not expected. Early galaxies were predicted to be small, faint, and inefficient. Models assumed star formation would begin slowly, building momentum over hundreds of millions of years. MOM Z14 violates that assumption immediately. The galaxy is already forming stars at a significant rate. Even more telling, its light shows traces of nitrogen. Nitrogen does not appear in the first stars. It requires stellar processing. Stars must form, burn, and return material to their surroundings before nitrogen becomes visible. That means at least one earlier generation of stars already lived and died before the light we now observe was emitted. All of that happened within less than 300 million years. To put that into perspective, Earth is 5 billion years old. Dinosaurs existed for about 165 million years. This galaxy completed multiple stellar cycles in less time than dinosaurs existed on Earth. This compresses cosmic timelines severely. The explanation begins with conditions unique to the early universe. Space was smaller. Matter was denser. Gas clouds were closer together. Gravity had more material to work with in less volume. Collapse happened faster. Dark matter played a central role. Invisible halos formed first, acting as gravitational anchors. Gas fell into these halos and compressed. Once density crossed a threshold, star formation ignited rapidly. This process was expected. The speed was not. Star formation models rely on feedback. When stars form, they emit radiation and explode as supernova. That energy pushes gas away, slowing further star birth. In the early universe, feedback appears weaker or delayed. Gas collapsed faster than it could be disrupted. The result was efficiency. James Webb data suggests early galaxies converted gas into stars far more effectively than modern galaxies do. The Milky Way forms a few new stars per year. Early galaxies formed stars across large fractions of their mass simultaneously. This shifts the narrative. The cosmic dawn was not a gentle sunrise. It was closer to a floodlight. Another consequence emerges when counting galaxies. Webb's deep field surveys reveal far more early galaxies than predicted. In some regions, the count exceeds expectations by factors of 5 to 10. This is not a calibration error. Multiple independent observations show the same pattern. The early universe was crowded. Crowding matters because it accelerates everything. More galaxies mean more interactions, more gas flows, more mergers, more opportunities for rapid growth. Structure builds structure. At this point, the universe no longer looks like a slow construction project. It looks like a system that reached critical density and ignited everywhere at once. This abundance also reshapes the idea of the observable universe's edge. The boundary is not defined by emptiness. It is defined by physics. Before stars existed, there was nothing to emit light. That is the real wall. James Webb is now approaching that wall. Theoretical models place the first stars at around 150 to 200 million years after the Big Bang. Current observations reach to about 280 million years. That gap is small in cosmic terms. It represents the last unlit chapter. Future observations will push closer. Surveys will grow wider. Exposure times will increase. The remaining darkness will shrink. The significance of the cosmic dawn extends beyond curiosity. These first stars change the universe permanently. Their radiation ionized surrounding gas, transforming neutral hydrogen into plasma. This process, called reionization, altered how matter behaved on large scales. Ionized gas resists collapse. After reionization, small gas clumps struggled to form stars. This explains why many low-mass dark matter halos today remain dark. The cosmic dawn shut certain doors while opening others. Everything that followed: galaxy clustering, star formation rates, chemical enrichment, was shaped by this early burst of activity. James Webb does not just show that the universe lit up early, it shows that once the light turned on, it did not hesitate. The universe reached complexity faster than expected, and this speed creates tension with another assumption: mass. If galaxies form this early and this efficiently, then something even more extreme must also be happening at their centers. That is where the next problem appears. In the earliest galaxies, something is growing faster than stars themselves, and it should not be possible. When astronomers began measuring the centers of these early galaxies, a deeper problem emerged. Galaxies were not the only structures growing faster than expected. Something at their cores was outpacing everything else. Supermassive black holes were already present, already active, and already far too large for the age of the universe they lived in. A black hole forms when a massive star collapses. A typical stellar collapse produces a black hole with a mass tens of times that of our Sun. That is the starting point. Growing from that to a black hole weighing millions or billions of solar masses requires time. A lot of time. Physics places a limit on how fast this growth can happen. That limit is called the Eddington limit. It describes a balance point where the outward pressure of radiation from hot infalling matter equals the inward pull of gravity. Beyond this rate, radiation pushes gas away faster than gravity can pull it in. Under this limit, a black hole increases its mass by about 1% every million years. At that pace, growing from a 100 solar mass seed to a billion solar mass giant takes roughly 700 to 800 million years, assuming uninterrupted feeding at the maximum allowed rate. Now compare that to what James Webb is observing. Webb has confirmed galaxies less than 600 million years after the Big Bang that already host black holes weighing millions of solar masses. Some are even larger. This leaves no margin. There is not enough time in the cosmic clock. One such system is CANU CS LRDZ 86, observed when the universe was around 570 million years old. Spectroscopic data shows intense radiation from its center, a clear signature of an actively feeding black hole. The inferred mass of that black hole rivals or exceeds the total stellar mass of the galaxy itself. For context, in the modern universe, the central black hole typically weighs about 0.1% of the galaxy's stellar mass. In this system, the ratio is close to 1. The center dominates. The galaxy is almost an accessory. This inversion is not subtle. It represents a fundamental breakdown of the assumed coevolution between galaxies and their black holes. The situation becomes even more extreme when looking at how fast these black holes are feeding. James Webb, combined with X-ray observatories, has identified black holes consuming matter at rates exceeding the Eddington limit by factors of 10 to 40. One object, known as LID 568, is feeding at over 40 times the theoretical maximum. To make that number tangible, imagine a car designed to safely drive at 100 kilometers per hour. LID 568 is moving at 4,000 kilometers per hour without disintegrating. The equations say this should not happen. The data says it does. The explanation likely lies in short, violent growth episodes. In the early universe, gas was abundant and dense. Galaxies were chaotic and unstable. Under these conditions, gas could collapse onto a black hole from many directions at once. radiation pressure, normally effective at halting infall, becomes overwhelmed. These events are known as super-Eddington accretion bursts. They are inefficient in terms of energy balance, but extremely efficient in mass gain. A black hole can double its mass in a few million years during one such episode. James Webb's importance here is not theoretical. It has directly observed the spectral signatures of this process. Highly ionized gas, broad emission lines, extreme luminosity. These are not simulations. They are measurements. This suggests that early black holes did not grow steadily. They grew in fits, short periods of explosive feeding followed by quieter phases. Stack enough of these bursts together, and the mass problem begins to resolve. Another possibility shifts the timeline even earlier. Some black holes may not have started as stellar remnants at all. They may have formed directly from collapsing gas clouds, weighing thousands to tens of thousands of solar masses. These so-called direct collapse black holes bypass the star phase entirely. They start heavy. If a black hole begins its life at 10,000 solar masses instead of 100, the growth problem becomes much easier. James Webb has not yet observed a direct collapse black hole forming, but it has observed galaxies whose properties strongly suggest their existence. Extremely compact systems, minimal stellar populations, overmassive black holes with little surrounding structure. The universe appears to have experimented with multiple formation pathways early on. Some black holes grew from stars. Others may have skipped that step entirely. The key realization is this: black holes were not passengers inside galaxies during the cosmic dawn. In many cases, they were drivers. This reshapes how scale should be understood. Galaxies were not always the dominant architects of structure. In the early universe, gravity concentrated itself quickly, and black holes exploited that concentration efficiently. There is another layer to this story, and it makes the scale problem even more unsettling. James Webb has found entire populations of compact objects known as little red dots. These are small, distant, intensely red galaxies that appear far brighter than their size should allow. Hundreds have been identified so far. Each one is either impossibly dense with stars or powered by a disproportionately massive black hole. Both options strain physical limits. Stellar densities high enough to explain the brightness would cause frequent collisions and mergers between stars, something not observed today. Black hole explanations require extreme mass ratios. Either way, the early universe was producing compact, energetic systems at a rate no model predicted. What this reveals is not just faster growth, but earlier hierarchy. Centers formed early. Gravity organized matter inward before spreading it outward. The universe built its cores first. This changes how scale should be visualized. The early universe was not a diluted version of today's cosmos. It was a compressed, aggressive environment where mass rushed toward centers and ignited rapidly. James Webb does not show a universe slowly assembling from the edges inward. It shows a universe that lit its engines early and sorted out the details later. The implication is profound. If black holes shaped galaxies from the beginning, then the growth of structure across billions of light years was influenced by compact objects formed within the first few 100 million years. Scale, in this sense, is not just spatial. It is hierarchical. Small regions of extreme density dictated the evolution of vast regions of space. And this brings the question to its sharpest point. If galaxies and black holes grew this fast, this early, and in such numbers, then the universe was not just large. It was efficient at becoming large. That efficiency must leave fingerprints not only in individual objects, but in the overall architecture of the cosmos. Those fingerprints appear when we zoom out, far out, into the large-scale structure itself. Once astronomers stepped back from individual galaxies and black holes, a larger pattern began to emerge. James Webb was not just finding strange objects in isolation. It was revealing how matter itself arranged across enormous distances far earlier than expected. The issue was no longer about single galaxies forming too fast. It was about structure appearing before the universe should have been ready for it. In modern cosmology, structure forms hierarchically. Tiny density fluctuations left over from the Big Bang grow slowly under gravity. Dark matter collapses first, creating invisible scaffolding. Gas follows, cooling and settling into these gravitational wells. Stars ignite. Galaxies emerge. Over billions of years, galaxies gather into groups into clusters, and clusters connect through filaments to form the cosmic web. This process is slow by design. Gravity is weak on large scales. It needs time to amplify small differences into large structures. James Webb shows that time was apparently not required in the amounts we assumed. Deep field surveys reveal galaxy overdensities, regions where galaxies cluster together, at redshifts above 8 and 9. When the universe was less than 600 million years old, to visualize the scale, imagine pouring a teaspoon of ink into a swimming pool. At first, the ink disperses slowly, forming faint streaks. It takes time for patterns to appear. Now imagine the same ink forming visible tendrils almost instantly. That is what Webb is observing. Matter organizing itself far faster than expected. In one James Webb survey field, astronomers identified multiple galaxies separated by only a few 100,000 light-years, all at nearly the same redshift. This implies they formed in the same gravitational environment. The universe was already building neighborhoods, the simulations that predicted smooth. Sparse early structure now underproduced these environments by factors of 5 to 10. This discrepancy becomes clearer when considering scale growth. At 300 million years after the Big Bang, the universe was roughly 1/10 its current size. Distances were compressed. Matter density was much higher. Under those conditions, gravity had more leverage. James Webb data suggests that this density advantage mattered far more than expected. Dark matter halos collapsed quickly. Gas followed immediately. Star formation ignited almost simultaneously across entire regions. The result was synchronized growth. Galaxies did not form alone. They formed in waves. This explains why Webb repeatedly finds too many galaxies in every deep field. It is not just that galaxies formed early. They formed together. Large-scale structure was not waiting politely for billions of years. It was already sketching itself into the universe, while the cosmic clock was still near zero. Another clue comes from gravitational lensing. Webb often uses massive galaxy clusters as natural magnifiers. These clusters bend space-time, amplifying the light of galaxies far behind them. The lensing maps show that even at early times, mass was already concentrated into coherent regions, large enough to warp space-time measurably. These are not weak distortions. Some background galaxies are magnified by factors of 10 to 50. For lensing to be that strong, the foreground structures must already be massive. That mass had to assemble quickly. This suggests that the cosmic web, the filamentary network connecting galaxies across hundreds of millions of light-years, began forming much earlier than expected, not fully matured, but unmistakably present. James Webb does not show a smooth early universe with isolated points of light. It shows texture, patterns, organization. This changes how true scale should be interpreted. The scale of the universe is not only about size in kilometers or light years. It is about how fast complexity appears across those distances. A universe that takes billions of years to organize feels large. A universe that organizes itself in a few 100 million years feels aggressive. This leads to an uncomfortable implication. If structure formed early and efficiently, then the observable universe is likely only a small, already structured slice of something much larger. The cosmic web we see may extend far beyond what light has had time to reach us from. The PAT, James Webb, strengthens this realization by showing that even tiny sky regions contain thousands of galaxies. A patch the size of a grain of sand held at arm's length contains tens of thousands of galaxies. Scale stops being intuitive at this point. Numbers lose meaning. What remains is pattern. The universe is not just big. It is densely patterned at every scale we can observe. Wherever Webb looks deeper, it finds more structure, not emptiness. This suggests a principle. Complexity is the default outcome, not a late-stage accident. And if that is true, then the early universe was not a blank canvas slowly filling in. It was a compressed engine, already running hot, already assembling vast architecture long before we arrived to notice it. The next question follows naturally. If structure formed this early, and light from that era still reaches us, then what we call the edge of the universe is not an edge at all. It is a horizon created by time. James Webb is showing how close that horizon really is. At first glance, the numbers seem incompatible. The universe is about 8 billion years old. Yet, the observable universe spans roughly 93 billion light-years in diameter. This sounds like a mistake, or a trick of math. James Webb has made this contradiction impossible to ignore, because it is now filled with real objects instead of abstract numbers. Light travels at a fixed speed. That part is simple. If light has been traveling for 8 billion years, then intuition suggests the farthest visible objects should be about 8 billion light-years away. But the universe did not remain the same size while that light was traveling. Space itself expanded. Imagine drawing two dots on a rubber band. One dot represents a galaxy. The other represents Earth. Light leaves the galaxy and begins its journey. While it travels, the rubber band stretches. The distance between the dots increases even though the light is already in motion. By the time the light arrives, the distance between the starting point and the destination is far larger than when the journey began. This is why the observable universe is much larger than its age, measured in light years. James Webb brings this abstraction into focus by showing galaxies whose light began its journey when the universe was only 200 to 300 million years old. At that time, those galaxies were relatively close, measured in tens of millions of light years. During the next 13 billion years, space expanded dramatically. The same galaxies are now tens of billions of light years away. The number 93 billion light years describes the current distance between the most distant observable regions, not the distance light traveled. Light from those galaxies traveled about 13 billion light years, but the space it moved through kept stretching. This distinction matters because it reveals something deeper about scale. The universe does not behave like a static container with objects moving inside it. The container itself grows. James Webb's role here is crucial. Older telescopes saw the early universe as sparse and faint. Webb shows it as populated and structured. When the early universe contains many galaxies, black holes, and forming clusters, the scale of expansion becomes tangible. The expansion did not stretch empty darkness. It stretched matter, radiation, and structure. Another number sharpens this realization: the cosmic microwave background. The oldest light we can observe comes from about 380,000 years after the Big Bang. That light originated from a region now roughly 5 billion light years away in every direction. That region has been carried outward by expansion for almost the entire age of the universe. James Webb cannot see that far back. There were no stars yet, but it bridges the gap between the cosmic microwave background and the first galaxies. It fills the early universe with structure up to the horizon. This creates a continuous timeline. Radiation first, then stars, then galaxies, then clusters. The scale grows at every step. The illusion lies in thinking the observable universe has a meaningful edge. The edge is simply where light has not had time to reach us yet. Beyond it, the universe almost certainly continues, with similar patterns. James Webb reinforces this idea by showing that every time observation depth increases, the universe looks more crowded, not less. There is no trend toward emptiness near the horizon. Density does not fall off. Structure does not thin out. This strongly suggests that the observable universe is a sample, not a boundary. A volume defined by time, not by physical limits. To grasp this intuitively, consider Earth's horizon. Standing on a beach, the ocean appears to end a few kilometers away. Ships disappear beyond that line. The horizon feels like an edge, but it is created by geometry, not reality. The ocean continues far beyond what you can see. The cosmic horizon works the same way. James Webb is effectively climbing higher ground, extending the line of sight. Each extension reveals more ocean. This changes the meaning of true scale. The universe is not just 93 billion light-years across. That number describes the size of what has had time to communicate with us. The full extent may be vastly larger, potentially infinite. Webb cannot prove infinity, but it removes every observational hint of a finite boundary. There is one more subtle consequence. Because expansion accelerates due to dark energy, some galaxies visible today will eventually disappear beyond our horizon. Their light will stretch so much that it never reaches us again. The observable universe is not only growing, it is also losing parts of itself. James Webb is capturing a snapshot of the universe at a special moment, late enough that structure has formed, early enough that much of it is still visible. The scale we see now is not permanent. This realization reframes the discoveries. Webb is not merely showing how big the universe is. It is showing how fast the universe becomes unreachable. And that raises a deeper question. If the observable universe is defined by time, not size, then what does it mean to say we are seeing the universe's true scale at all? The answer lies not in distance, but in density, in how much exists within any given patch of space, and James Webb has made that density impossible to ignore. Once distance is no longer the main surprise, density takes its place. James Webb does not merely push the horizon outward, it compresses reality inward. Every deep field image delivers the same message. Wherever the telescope looks carefully enough, the universe is packed. Consider a patch of sky the size of a grain of sand held at arm's length. That area corresponds to roughly 1/10,000,000th of the entire sky. When James Webb stared at such a region during its early deep field observations, it revealed thousands of galaxies. Not stars. Galaxies. Each containing billions of stars. This is not an exaggeration or a metaphor. It is a measured count. If that density were uniform across the sky, and observations suggest it is, the observable universe contains over 2 trillion galaxies. Even if that estimate is off by a factor of 2, the conclusion remains unchanged. The universe is not sparsely populated. It is saturated. James Webb makes this saturation visible because of how it collects light. Older telescopes captured brief exposures of distant regions. Webb stares for hours or days. Photons arrive slowly from the early universe, sometimes one at a time. Webb's detectors accumulate them patiently until a galaxy emerges from noise. This process turns darkness into structure. The shock comes from realizing that most of the universe was invisible to us, not because it was empty, but because it was faint. When sensitivity increases, emptiness dissolves. To visualize this, imagine flying over a city at night with a dim camera. You see a few bright lights, turn up the sensitivity, and suddenly entire neighborhoods appear. Streets, buildings, patterns. The city was always there. James Webb is turning up the cosmic sensitivity. The implications reach beyond counting galaxies. Density affects gravity, star formation, and black hole growth. In a dense environment, interactions are frequent. Galaxies pass near one another. Gas flows along filaments. Mergers happen early. This explains why Webb sees galaxies evolving quickly. High density accelerates everything. The early universe was not just smaller. It was tighter. Matter had less space to spread out. That compression made gravitational collapse efficient. Structures assembled rapidly because they did not need to pull matter from far away. This density also explains the abundance of massive objects early on. Dense regions produce massive stars. Massive stars collapse into black holes. Dense gas feeds those black holes aggressively. The universe did not need patience. It had proximity. James Webb reveals that density persists across scales. Zoom in on a deep field, and galaxies fill the frame. Zoom out, and those galaxies trace filaments connecting clusters across hundreds of millions of light years. Density at small scales feeds density at large scales. This nested structure is key to understanding true scale. The universe is not a thin scattering of objects across vast emptiness. It is a hierarchy of crowded systems, embedded inside even larger crowded systems. Even the spaces between galaxies are not empty. They contain diffuse gas, dark matter, and radiation. Webb can trace some of this gas through emission lines and absorption features. Intergalactic space is thin, but it is not nothing. Another number sharpens the picture. The average distance between galaxies in the early universe was only a fraction of what it is today. Expansion has stretched those distances by factors of 5 to 10 since cosmic dawn. What looks like isolation now was once close proximity. This proximity likely contributed to the speed of chemical enrichment. Metals produced in early supernovae did not have far to travel. They spread quickly, enriching neighboring regions and enabling subsequent generations of stars to form planets sooner than expected. James Webb observes galaxies less than 300 million years old, already containing elements like carbon, nitrogen, and oxygen. That means multiple generations of stars lived and died in a very short time. High density made that possible. Density also reframes the question of habitability. A dense early universe was hostile, dominated by radiation, frequent supernovae, and active black holes. As expansion continued and density dropped, calmer environments emerged. The universe aged into habitability. We exist in a low-density era. That is not accidental. It is a phase transition. James Webb is showing both sides of that transition. The packed, violent youth, and the calmer, structured maturity. This leads to a crucial insight. The universe's true scale is not just how far it extends, but how much happens everywhere. Large scale is not empty scale. The density shock forces a reassessment of intuition. Vastness does not imply loneliness. Size does not imply sparsity. The universe is large because it contains an enormous amount of structure, not because it contains a lot of nothing. And if density remains high near the observable horizon, then beyond it likely lies more of the same. More galaxies, more filaments, more structure. The observable universe does not look like a thinning edge of existence. It looks like a slice through a much larger, consistently populated whole. James Webb has not just expanded our view, it has dismantled the assumption that deep space is mostly empty. The next realization is even more unsettling. If density and structure appear everywhere we can see, then the observable universe may not be special at all. It may be statistically ordinary. And that raises the question of scale beyond observation. As the data accumulates, a quiet but radical idea begins to take shape. Nothing James Webb observes near the edge of visibility looks unusual. The galaxies are not thinning out. Their properties are not degrading. Their arrangements remain structured. Their densities remain high. From a scientific perspective, this is unexpected. Boundaries usually announce themselves through change. Instead, the universe looks statistically consistent. In many areas of science, when a system shows no trend toward special behavior at its limits, the safest assumption is that the region being observed is not unique. James Webb's deep fields suggest exactly this. The observable universe behaves like a typical region sampled from something much larger. This is known informally as the ordinary universe hypothesis. The idea is simple. If the observable universe were close to a physical edge, conditions near that edge would differ. Structures would thin, density would drop, evolution would look incomplete. None of this appears. Every deep field shows galaxies at multiple stages of development, all embedded within larger structures. The patterns repeat. To appreciate why this matters, imagine drilling a core sample into an iceberg. If every layer shows similar ice structure, similar density, similar composition, the sample likely does not come from the edge. It comes from somewhere interior. The iceberg is larger than the sample. James Webb's observations function as cosmic core samples. Another clue lies in uniformity. The cosmic microwave background shows that the universe is remarkably similar in all directions to 1 part in 100,000. That uniformity extends to galaxy counts and large-scale structure as far as observations allow. The same kinds of galaxies appear everywhere Webb looks. Uniformity across enormous distances suggests that the underlying process that built the universe operated globally, not locally. The laws of physics did not change near the horizon. Conditions did not degrade. This is important because the observable universe is not centered on any special location. Every observer, anywhere in the universe, would see a similar horizon centered on themselves. Each observer's observable universe would appear roughly the same. That symmetry implies something profound. There is no preferred vantage point, no cosmic center, no special location where scale behaves differently. James Webb reinforces this by showing that early galaxies near the observational limit resemble early galaxies found elsewhere. Their masses, brightness, chemical signatures, and clustering do not trend toward extremity. If the observable universe were close to the universe's edge, galaxies near that edge should look unfinished. They do not. This supports the idea that the true universe extends far beyond what light has reached us from. The observable universe becomes a bubble defined by time, not geography. There is another layer. Inflation theory predicts that the universe underwent a brief period of exponential expansion early in its history. During that phase, tiny regions were stretched to enormous sizes. If inflation occurred, the universe today could be vastly larger than the observable region, potentially many orders of magnitude larger. James Webb does not test inflation directly, but it is consistent with its consequences. Inflation predicts large-scale uniformity and repeating patterns across regions much larger than the observable universe. Webb sees repetition. The ordinary universe hypothesis does not claim infinity. It claims non-specialness. The part of the universe we can observe appears representative. This reframes the idea of true scale. The true scale is not a number like 93 billion light-years. It is the recognition that any number we measure is almost certainly an underestimate. James Webb has not revealed the universe's full size. It has revealed that there is no observational sign of a boundary. That absence is data. In science, what fails to appear can be as important as what does. And the missing feature here is an edge. The implication is unsettling. The observable universe may be one of countless similar regions, each containing trillions of galaxies, each evolving according to the same rules. Scale becomes multiplicative rather than additive. The universe may not just be large, it may be vast beyond repetition. James Webb does not confirm this directly. It cannot. But by showing consistency instead of decay at the horizon, it removes the strongest arguments against it. This sets the stage for a deeper problem. If the universe is this large and this ordinary, then the laws governing it must be robust across unimaginable distances and times. And yet, there is a growing sign that something in those laws does not quite add up. One scale appears ordinary and structure appears everywhere. Attention shifts to the mechanism, stretching it all apart. Expansion is not just a background process. It determines what becomes observable, what disappears beyond reach, and how the universe's size is inferred. Here, James Webb has quietly reinforced one of the deepest problems in modern cosmology. The universe is expanding. This has been known for nearly a century. Galaxies move away from one another, and the farther they are, the faster they recede. The rate of this expansion is summarized by a single number, the Hubble constant. In principle, this number should be the same, no matter how it is measured. In practice, it is not. One method measures expansion using the cosmic microwave background, the oldest light in existence. This approach looks at the universe when it was only about 380,000 years old, and projects the expansion forward using the standard cosmological model. It produces a value close to 67 kilometers per second per megaparsec. Another method measures expansion locally, using stars and supernovae in nearby galaxies as distance markers. This approach looks at the universe as it is now. It consistently produces a higher value, around 73 kilometers per second per megaparsec. The difference sounds small. It is not. Over cosmic distances, this discrepancy compounds into billions of light years. Two expansion rates imply two different universe sizes, two different ages, and two different histories. For years, astronomers suspected measurement error. James Webb was built, in part, to test that assumption. Webb observed the same distance markers used in local measurements: Cepheid, variable stars, and supernovae, but with higher resolution and infrared sensitivity. Dust, crowding, and calibration issues were reduced. If the earlier measurements were flawed, Webb would reveal it. It did not. James Webb confirmed the higher local expansion rate. The stars were at the distances previously measured. The numbers held, the tension remained. This result is subtle but devastating. It means the disagreement is not an observational mistake. It is physical. The universe appears to expand at different effective rates depending on how and when it is measured. This directly impacts scale. If expansion has changed over time in ways not captured by current models, then every distance estimate tied to those models becomes uncertain. The size of the observable universe, the timing of structure formation, and the interpretation of early galaxies all depend on expansion history. James Webb's discoveries of early, massive galaxies sharpen the problem. Faster early expansion makes early structure harder to form. Slower expansion makes it easier. The observations favor rapid structure formation, yet the expansion inferred from the early universe suggests otherwise. The pieces do not align cleanly. One possibility is that dark energy, the mysterious component driving accelerated expansion, is not constant. If its strength changed over time, early and late measurements would disagree. Another possibility is that an unknown component of the universe influenced expansion in the first billion years, then faded away. There is also the possibility that gravity behaves slightly differently on cosmic scales than current theory predicts. Even a tiny deviation would accumulate over billions of years into measurable differences. James Webb does not resolve this problem, but it removes the most comfortable explanation: error. This matters for the idea of true scale. Scale is not only about how far light has traveled, It depends on how space itself stretches over time. If expansion physics is incomplete, then every statement about size carries uncertainty. The universe may be larger or smaller than current models suggest, older or younger, more connected or more fragmented. Webb's role here is indirect but decisive. By validating both sides of the tension, early structure and local expansion, it forces the conflict into the open. The universe is not behaving exactly as the equations predict. That realization does something important. It reminds us that scale is inferred, not directly measured. It emerges from models that connect light, distance, time, and physics into a coherent picture. James Webb is testing those connections, and some of them are starting to strain. If our models struggle to describe the universe we can see, then extrapolating them to what we cannot see becomes risky. Which brings us to the final escalation. What James Webb implies about limits, knowledge, and the boundary between data and speculation. As James Webb pushes observation closer to the beginning of time, a paradox emerges. The telescope is revealing more of the universe than ever before. Yet, it is also clarifying where knowledge must stop. The boundary it exposes is not technological. It is fundamental. Every observation relies on light. Light needs time to travel. This creates an unavoidable horizon. Beyond a certain distance, events may exist, but their light has not had time to reach us. No future telescope, no matter how powerful, can overcome this limit. It is built into the structure of space-time itself. James Webb now operates close to that boundary. It observes galaxies as they existed only a few 100 million years after the Big Bang. Earlier than that, stars had not yet formed. Without stars, there is no starlight. Without light, there is nothing to detect. This is the first hard limit. The second limit is expansion, because space itself expands. Some regions of the universe are receding faster than light can cross the growing distance between us and them. Light emitted today from those regions will never reach us, no matter how long we wait. These regions are permanently, causally disconnected. The observable universe is therefore not just incomplete, it is forever incomplete. James Webb does not change this fact. It makes it visible. Each deeper observation approaches a surface beyond which information is inaccessible. The telescope is not revealing the universe's full story. It is revealing how much of that story is unreachable. This has consequences for the idea of true scale. If the universe extends far beyond what we can observe, then its full size is not a scientific quantity in the usual sense. It cannot be measured. It can only be inferred indirectly, through theory and consistency. Science remains grounded in data, beyond the horizon. Data ends. James Webb strengthens this boundary by showing that nothing unusual happens as the horizon is approached. There is no fade to emptiness, no breakdown of structure. The universe remains statistically consistent right up to the edge of observation. That consistency implies continuation, but it does not prove it. This distinction matters. In science, inference is not observation. It carries uncertainty. Another limit emerges from cosmic variance. The observable universe is a single realization of a much larger process. We cannot observe another universe to compare it with. Even if the laws of physics are universal, the specific arrangement of matter we see may be one of many possible outcomes. James Webb samples deeply, but it samples only one cosmic history. This places a ceiling on certainty. Some questions about scale will never have definitive answers. Is the universe finite or infinite? Does it repeat? Does it end? These questions may remain forever in the realm of models, not measurements. Yet this is not failure. It is clarity. James Webb shows that science advances not only by answering questions, but by defining which questions can be answered at all. The telescope delineates the frontier between what data can tell us and where speculation begins. Within that frontier, knowledge is expanding rapidly. Beyond it, humility is required. This reframes human curiosity. The universe is not obligated to be fully knowable. Its scale may exceed not only our instruments, but the very concept of verification. James Webb stands at this boundary, extracting the last photons that can reach us, converting ancient light into understanding. Each photon carries real information. Beyond them lies silence, not because nothing exists, but because nothing can speak to us. The true scale of the universe, in this sense, is not just large. It is partially inaccessible by design, and that realization leads naturally to the final act. What all of this means for cosmology, for humanity, and for our place inside a universe that is both knowable and unknowable at the same time. When all the discoveries are placed side by side, a pattern emerges that goes beyond any single galaxy, black hole, or measurement. James Webb has not simply extended our vision. It has altered the relationship between humanity and scale itself. The universe no longer feels like a distant backdrop. It feels active, crowded, and relentlessly productive. The early universe was not tentative. It did not hesitate, experiment slowly, or wait for favorable conditions. It built structure quickly, assembled galaxies aggressively, and grew black holes at a pace that strains our equations. The cosmos revealed by Webb is efficient. When conditions allow complexity, it appears immediately. This reframes age. 13.8 billion years sounds vast on human terms. On cosmic terms, it is sufficient to build trillions of galaxies, seed them with stars, enrich them with heavy elements, and arrange them into a web spanning unimaginable distances. Time, when combined with density and physical law, does not need to be long. It needs to be effective. Scale, then, is not defined by emptiness. It is defined by repetition. Everywhere Webb looks, it finds the same story told again and again with slight variations. Galaxies forming, stars igniting, black holes growing, matter flowing along invisible structures. The universe is not a sparse landscape with rare islands of activity. It is a continuous process unfolding everywhere at once. This makes our position clearer. Earth exists in a quiet era, in a low-density region, long after the universe's most violent growth phase has passed. That calm is not typical of cosmic history. It is a late condition, a privilege of timing. James Webb also forces honesty about limits. The true scale of the universe cannot be measured directly. It exceeds observation. It exceeds verification. What can be said with confidence is narrower, but still profound. The observable universe shows no sign of being special, incomplete, or near an edge. It looks like a fragment of something larger. That realization carries weight. If the universe extends far beyond what we can see, then human history occupies an infinitesimal region of space and time. Yet, within that region, the universe has produced something remarkable. The ability to observe itself. Atoms forged in ancient stars arrange themselves into instruments capable of reading ancient light. James Webb is not separate from the universe it studies. It is made of the same material, governed by the same laws, shaped by the same history. When it captures photons emitted billions of years ago, the universe is effectively examining its own past. This collapses the distance between observer and observed. The universe is not something happening elsewhere. It is something we are embedded within, participating in, and briefly aware of. The final message from James Webb is not about size alone, it is about context. We are not standing at the center of anything. We are not near the beginning or the end. We are not at a privileged scale. We are one moment in a much larger process, capable of understanding only because the universe allowed complexity to arise. The true scale of the universe is not fully contained in numbers like 93 billion light-years or 2 trillion galaxies. It is contained in continuity, in the fact that structure appears wherever conditions permit, in the fact that nothing we observe suggests a stopping point. There is no final answer here, only increasing resolution. James Webb has not closed the book on the universe. It has opened it wider than ever before, revealing that every page leads to more pages beyond. The data will continue to grow. The horizon will continue to shift. The picture will become sharper, then more complicated, then stranger again. There is no final edge to reach, only deeper understanding, followed by deeper mystery. And that, more than any measurement, may be the truest scale of all. What James Webb has shown us is not a finished picture, but a direction. Every new observation pushes the horizon back, not toward an edge, but toward more structure, more galaxies, more unanswered questions. The universe does not simplify as we look deeper. It becomes richer. There is still no final answer to the true scale of the universe. There is only data, and the data keeps growing. Each year adds clarity, and with it, new tension in our models, new surprises in places we thought were understood. That uncertainty is not a weakness of science. It is its engine. If the universe can build complexity so quickly, across such vast distances, then there is still far more waiting beyond what light has reached us from. James Webb has shown that the unknown is not empty. It is simply out of view. In the next chapter, we will follow where this data leads, into new physics, deeper time, and questions that may redefine what scale even means.